everyone. Let's solve another hard problem. So it should be solvable. 1168, optimize water distribution in a village. Again, haven't solved it before. Signature and houses in a village. We want to supply water for all the houses by building wells and laying pipes. For each house I, we can either build a well inside it directly with the cost wells I-1. Okay, 0 indexing and houses. Okay. So wells is an integer. Sorry, list of integers. I'm assuming. Or pipe in water from another well to it. The cost to lay pipe between houses are given by array pipes. Okay, so there is also pipes. Okay, so pipe will be a list of integers, and we need to return an integer. So I will write some tests, but first let me show the challenge. So the challenge here will be that for each house, you need to decide whether to connect it to another one or to build a well. And this essentially creates 2 to the power of n decisions, each of which can impact what we need to do otherwise. So what I don't understand yet is what does it mean that there can be several ways to connect to houses. Or piping water from another well to it. So it's not saying from the next house. It is saying that we can basically, we have a graph of pipes, and then we can select whichever is the cheapest one. I just thought about the implementation, the possible implementation solutions. I actually don't remember. I think it's Floyd Horschel. I'm afraid to be mistaken here, but this is like all and to and shortest paths. I'm just thinking whether we can use this Floyd-Warshall algorithm to figure out what's the minimum possible price that we are paying. Okay, so tests. Let's say we have houses like this, and I will just write the costs as like 2. Okay, how to even show this, because we have edge prices and also the costs themselves. So let's say 2, 5, 1, and we also have edge prices. Let's have here all edges. Okay, so let's say that this edge costs 1 and this edge costs 3. So if I'm not mistaken, then the minimum price to connect all houses would be 4, because we will build the well here and connect this price to this well, and the total price of this will be 3. And then there will be like this house that will just build another well here, and that will be it. So now let's also say that there can be a situation like this. So here we will be connecting the same here 3, but here we'll pay 7, just because I wanted to highlight that not necessarily our graph is connected. Okay, so let me now talk about the fluid Warshall algorithm. I think it's just like a small change, a small tweak to the fluid Warshall algorithm, because essentially we start with the default is building the wells everywhere, like in every house. But then we will be optimizing for what if there is a cheaper way to bring it into this particular house. So if the well if by default the well is being built, oh no, it won't work. So I was thinking that like in fluid Warshall we have a matrix of how cheap it is to get to like the shortest path from any to any other location, and based on our pipes we can calculate this situation. Like we can figure out what is the cheapest price, but I was thinking that we start with the diagonal, not of zeros, but of like whatever it costs to build a well here. But I guess not. So then let's say we run a fluid Warshall algorithm on top of our pipes, and we now have like between any two houses that can possibly have pipes between them, what would it be to build, what would be the cost to connect these two houses? So then we basically need to optimize can we write some dynamic programming? Dynamic programming for nth house. So dynamic programming where dp of I is actually two dps, right? dp building, and that's if we build a well in ith house. Oh, NGP no building. So the problem here is that if we decide that we want to build a well in a particular place, it also affects how cheap it can be for the houses that we have already considered. So it kind of defeats the purpose. Can there be some greedy algorithm? Yeah, I think it can be some greedy algorithm. Greedy. Cheapest well. Yeah, start by building the cheapest well. Then after you have built it, you can use a heap heap for cheapest wells. So yeah, actually here, let's say we start with the cheapest well. We use the heap and we just add all the neighbors of this so we have built a well here, and then we also know the price of the wells for all our neighbors, and we can either we can prioritize. We can put new options for the neighbors who can who now like are considering building their own wells, but now we have built this well, and if we can bring water there for a cheaper price, we just do that, and we can update their wells prices, and we uh, push new values to our heap, and we continue iterating, and we always just retrieve the cheapest possible well price. And it will be overall and figuring out runtime and figuring out whether we can optimize this. It's kind of like Dijkstra algorithm, but a little different. It's as if it's a Dijkstra on a graph where we start at an outside node, and this node is connected by the price of well building to all the other nodes, but all the other nodes are also connected one to another, and we just we consider this bigger graph, and that's why all of the nodes are already in our frontier when we start, because all of them are neighbors of this like outsider node. Okay, and then this means that our frontier is already of the size of, and let's say there are n houses and m edges as usual. So it will be for each house, finding the shortest path would be of n log the biggest possible size of this heap would be n plus n. Yeah, I think so. I think this will be it. So we don't need Floyd-Warshall algorithm. It doesn't help us. Okay, now let's do the implementation. Oh yeah, in space, right? So this is runtime. This is basically the size of the frontier. We start with log of n for each operation, and well, actually, we might need more than n operations at most. What if we have like some node that is unconnected and that is longer than all the other possible combination of nodes? So we will be treating over this whole frontier that can grow to a size of n plus m. So we n plus m multiplied by log n plus m runtime, and space will be also n plus m. Okay, implementation, let's see. Will be wells copy, and frontier will be wells copy, and here, oh no, it won't be just wells copy, it will be And just to be sure, so okay, so we start counting houses at 1. So for frontier, we will have I plus 1, and this will be the house number, but the price will be cost for I cost new wells. Heapify frontier. And now, what do we need to do? We need to also create a graph. Will be okay, so these are all the preparations, I think. Now we just need to run the extra. Let's just call it main cost. So for while frontier, we do cost house equal heap q heap pop frontier. Then let's write it in such a way that we don't need to do anything at this point. We already have defined it as a minimal cost at this point. So if this cost was ever pushed to the frontier, it's already is presumed to be the minimal one. So this will be our invariant here. So here we just need to iterate over the neighbors. So for neighbor in graph house, for neighbor edge pipe cost, if cost plus pipe cost is smaller than mean cost neighbor, then obviously we want to push this now. and update it. So we do first in cost will be equal to cost plus pipe cost, and then we also do frontier here q push frontier. We will be pushing this value and neighbor. So we are updating right away so that we are never adding, like always just adding the things that are even better. And it might be that, oh, actually, I think we can tweak this algorithm a little bit. So decided equals false times length. Oh, actually, I also need to change here. It's not neighbor, it's neighbor minus 1 here. So here is what I will do. We don't want to process neighbors each time we get to the same neighbor. We can push several times to this frontier. So once we have popped a specific house, it's definitely the invariant is that it's the smallest possible cost that can be, and we have decided on this neighbor it can never be cheaper than that. So this will not improve the algorithm runtime, but it will be realistically better. So we can update decided of house minus 1 equals true, and here we'll do if continue. We just don't even waste our time on the neighbors because we can never do better. We have already processed this neighbor. Okay, now I think that's it. Return sum. Oh. This is incorrect. That depends on some assumptions. So it's the cost to build pipes. So if we have already built a pipe for some of the neighbors, we don't need to build this pipe again. Actually, this whole solution seems to be incorrect because of that. what I'm trying to say. Let's say we have something like this, right? And we have one here and one here. And we also have some like longer edge between 1 and 3. Let's say it just costs 1. So what would be the total cost here? We are expanding from 1, and here the cost will be 1. And then we are adding both neighbors, which are, let's say it's 5. 1 plus 1 plus 2 is 4. 1 plus 6. So to demonstrate what I'm trying to say will be this. What will be the total cost here? So we are paying 1 here, and we are paying 1 here, and we are calculating. Okay, so first we are expanding there, and it will be 1. Then we have two neighbors, 2 and 4, and here it will be, let's say, 3 actually. So 1 and 1 will be cheaper than 3, so we are expanding here, and the total price will be 1 plus 1, 2. Then we are expanding this node further, like it will be getting to, yeah, actually there will be like 6 will be one price, and then 1 plus 4 another price, 5, and then 1 plus 1, 2, plus 2, 4. This will be another price. So we expand this 4, and the total price will become 4 to connect this whole thing. But for each individual one, the minimal cost will be 1 here, and 2 here, and 4 here. So it will be like min cost will be a sum of those. But we just pay this cost once, and need to pay this cost once. So how do we calculate the minimum costs in the end? I think the invariant here is that we are always building the connection, whichever we need. To connect the particular house with the minimal cost. Can it be that we haven't built some connection? So I think it can never happen that we have found a minimum cost, but don't have all of the connections built. Like, if we find that this is the minimal cost and we don't need to build this connection, it basically assumes that the previous connection that we have here is already built. Because it would be cheaper to get here, and if we got here at this price and now we can build this connection, it will be also the cheapest one. So okay, now we just need to add this value to the minimal cost at this point, and because of that, minimal cost will be working differently. Minimal cost will be and cost will be 0. And here we are doing something different. We are also doing this. So this is the price of the last connection that we are building, that we need to build to get here. Oh, actually, it will be cost here, right? Yeah. So to get here, like from wherever else, we need to build this cost, and then we do what? Neighbor and pipe cost. And then once we have decided here, once we decide about the house cost, house type cost, marginal cost, so the cost that we are adding, and then here it will be cost plus marginal cost, and here we will be returning not sum of mean cost but just mean cost, so that we are not counting the prices of everything twice. Okay, have already spent how much? 40 minutes almost on this problem. Because we are exhausting all of the whole frontier, we'll always get even to the non-connected things, because they are connected to our external node. And let's maybe see how this whole thing will work for this graph, right? So let's copy it here. And I will also check if I have made any stupid mistakes on the way. Okay, so first of all, we are creating a frontier. Now our frontier becomes cost of 2 to build to 1 and the marginal cost of 2. Then actually we start with cost of 1 to build to third house and the marginal cost of 1, and there will be cost of 5 to build to the second with a marginal cost of 5. So it's keepified. Here I think it's clear what it will be, and decided false length values. Okay, so false, false, and cost will be equal 0. The frontier, so okay, first of all we pop this element, and for this element we decide if decided. Okay, this is not decided, so we continue, and first of all we set the decided by house. House is the third one, so it becomes decided. and mean cost will be equal to marginal cost. We are building this price of one element, so it will become 1. Then for neighbor and pipe, we have neighbors, this one, right, just one, and it will be cost plus pipe cost. It's actually smaller than the current cost, right, because it will be 2, 5, and 1, sorry, 5 and 1, and we are basically proposing to build it in 1 and 3 and 4. So what do? We update it first to cost plus pipe cost, okay, and then we are pushing another value to this. What will it be? It will be here, it will be 4 to get to the house 2 at the marginal cost of 3, because this pipe will be costing 3. And now we do what? We pop another element, and this another element becomes this, and it's decided. No, it's not decided. So we update the house number 1 to true. We have built a well here, and mean cost plus or equal marginal cost, which will be 2, so total is 3. And then for neighbor, which is just one neighbor, and it's again is smaller cost, so 3 to get to the house 2 at the marginal cost of 1. And we now update our heap and we iterate further, so we finally get this element from our frontier, which is house 2, and house 2 is decided. Okay, so now minimum cost will be marginal cost 4, and for all the houses or all the neighboring houses, they will always already have smaller cost than cost plus pipe cost, so we are not updating this, and we are updating this decided. So theoretically at this point we can also just change again, improve our algorithm without actually improving it. In terms of runtime, we can stop whenever we have like decided that is equal to this, like if all houses are decided, we can count the number of decided houses, but it will not change the running time. However, just decided equals 0, equals 1, undecided equals 1, and while frontier and undecided smaller than length. Okay. This looks reasonable. Oh, in costs. Incorrect. Let's see if that's mistaken logic or mistaken in thinking, in implementation. So here we have this well, and the minimum price will be 1 plus 1 plus 1, right? So it's 3, but we are saying 5. Oh yeah. So we are not processing this correctly, right? So we also need to get elements on the top with a smaller marginal cost, and we are adding to the top with a smaller house number. Yeah, essentially. The house numbers will be equal in this case. This is interesting. I think it should be correct, but it's not. Yeah, I see what's the mistake here. This. Because if it's equal, you can also update, and the smaller marginal cost will be showing up on top. And then this will become K4. That is interesting. Let's print this again. Okay. Let's also change the ordering. So here we're expanding 1. Now we can get to actually it's incorrect either way, even if we have something like 1, 1, 2, here 3, right? So the cost will be compare marginal costs. Because if it's 1, 1, 2, so in total it will be 4. But building this 1 plus 1 plus 2 is cheaper than building 1 plus 1 plus 3. Even though this thing will be more expensive. Does it mean that we should only add marginal costs? Only process marginal costs to connect things? Yes, looks like it. We don't care about the cost at all. We only care about the marginal cost. It just work if I remove this. Okay. Wow. Yeah. Tough problem. Thanks everyone. See you tomorrow.